In this video, we're going to talk about one-sided limits. Now, we've already discussed this to some degree in our initial video lesson regarding limits, but we'll go over some of these key topics again. First of all, when we talk about the limit as x approaches a being a real number from the left-hand side, we write it like this. Okay, that little superscript, the minus sign indicates we're approaching from the left, and when we're approaching from the right, we indicate it like that. And so something we learned in a previous video was that if the limit as x approaches a from the left of f of x equals b, where a and b are real numbers, and if the limit as x approaches a from the right of f of x equals b, then we can say the limit as x approaches a of f of x equals b. This last statement, the one I'm pointing to with an arrow, that's not a one-sided limit, that is the limit. But if we can say that one of the one-sided limits exists and the other one-sided limit exists, but those two one-sided limits don't equal each other, well then the limit as x approaches a of f of x does not exist either. Okay? So we're going to recall from a previous slideshow some of our limits that we've looked at before. What we're going to do is we're going to show that the limit as x approaches 1 of this piecewise function does not exist, or we're going to evaluate it. And the way we're going to do that, we can look at it graphically. We can graph the first part of the piecewise function and the second part of the piecewise function as well. And now we can say, what if we have the limit as x approaches -1 from the left of f of x, and we can see that that equals 2, or sorry, -2, because as x is approaching -1 and we're tracing over the function, our y-coordinate is going to get infinitely close to -2. But as we approach an x value of -1 from the right-hand side, we're going to see, oh, there it is. So we're going to see that our y-coordinate is going to get infinitely close to -3. And so since those two one-sided limits don't agree with each other, we can say that the limit as x goes to -1 of f of x does not exist. We can look at this one as well. This is a little reminder of something we talked about in an earlier slideshow. We can't actually determine the limit as x goes to 2 from the left of that function. We can't determine it because literally there is no from the left. Like everything from the left, the function literally doesn't exist. We can't approach it. So we can only approach it from the right, as that arrow shows. As we get infinitely close to an x value of 2 from the right-hand side, our y-coordinate gets infinitely close to 3. Okay, and so the one-sided limit exists. So since that's the only direction from which we can approach this x value, therefore we state that the value of the one-sided limit is the value of the limit itself. We can't approach from both sides, so we don't have to compare the two one-sided limits because one of them doesn't exist. Okay, so we can say the limit overall as x goes to 2 of f of x equals 3. Now, what if we wanted to evaluate right here the limit as x goes to 0 of the absolute value of x? Well, we can draw a diagram. We see as we approach 0 from the left-hand side, our y-coordinate is getting infinitely close to 0. And as we approach 0 from the right-hand side in this diagram, the y-coordinate's getting infinitely close to 0. So we know the two one-sided limit values. So they both agree with each other, and we can say the limit as x goes to 0 of the absolute value of x is equal to 0. Now let's see if we can evaluate this next one. This is a pretty interesting question. Let's think about absolute values for a second. We know that when w is greater than 0, the absolute value of w is w. So for instance, if I said to you, what's the absolute value of 7? You'd say 7. If I said, what's the absolute value of 3? You'd say 3. And if I said, what's the absolute value of 0? You'd say 0. In other words, if the number we're putting inside is greater than or equal to 0, then the absolute value of that number is just that number. Okay. Now, this next one's a little bit different, a little bit harder to see perhaps, but let's think about it. Suppose w is less than 0. So let's imagine for a second w is negative 6. We're trying to find the absolute value of negative 6. Well, most people will tell you the absolute value of negative 6 is 6. Okay, no problem. But I want you to imagine that I need you to state it in terms of negative 6. I need negative 6 to be part of your answer. Well, after a moment or two of thought, you might say, well, then I'll just put a negative in front of it. And certainly the negative of negative 6 is 6. So if I said to you, what's the absolute value of negative 3? And I said you must have a negative 3 in your answer, you'd say, okay, let's call it negative of negative 3. Okay? So what we're trying to say here is if I tell you w is less than 0, just like it was in one of these questions, and then I say to you, what's the absolute value of w? Well, just like you did a moment ago, you just put a negative in front. Okay? So that might take a moment or two of contemplation, but what we end up with is this rule. And right here, what I'm circling in red there is something that you really need to understand in order to know how to do this question. And similarly, if you look at what I'm circling here, which is a little bit more apparent, that's something you need to know. Okay? So we've written them both in red there, very important points. So we're going to let w for a moment equal x minus 4. Now, when w is greater than or equal to 0, that's like saying x minus 4 is greater than or equal to 0. In other words, we're going to let the interior part of that absolute value be greater than or equal to 0. Well, x minus 4 being greater than or equal to 0 is another way of saying x is greater than or equal to 4. Or when x minus 4 is less than 0, that's another way of saying x is less than 4. So we're going to say when x is greater than or equal to 4, and x minus 4 is therefore greater than or equal to 0, the absolute value of x minus 4 is x minus 4. And this goes back to what we said here. When the interior part is greater than or equal to 0, the absolute value of it is itself. However, when w is less than 0, then the absolute value of w equals w. So in other words, when x is less than 4, then x minus 4 is less than 0, which means the absolute value of x minus 4 is negative of x minus 4. Distributing that negative sign in, we get negative x plus 4. Okay, and again, it might take a moment or two of contemplation. But what we can come up with then is the following. The absolute value of x minus 4 is the same as negative x plus 4 when the interior x minus 4 is less than 0. In other words, x is less than 4. And it's equal to x minus 4 itself when the interior is greater than or equal to 0. In other words, when x is greater than or equal to 4. Okay, so since that's true, then we can say that x minus 4 over x minus 4, absolute value of x minus 4 over x minus 4, when x is less than 4, is like saying negative x plus 4 over x minus 4. Well, negative x plus 4 is the same as negative bracket x minus 4. This is just a common factoring step. Over the denominator, we cross out these two factors here. We get negative 1 over 1, which is negative 1. In other words, when x is less than 4, we're saying the absolute value of x minus 4 over x minus 4 is actually equal to negative 1. But when x is greater than or equal to 4, then the absolute value of x minus 4 over x minus 4 is x minus 4 over x minus 4. We can cancel out those factors. 1 over 1 equals 1. Okay? But now keep in mind, x can't actually equal 4. Because if x equaled 4, we'd have a 0 in the denominator. So what we're really saying is when x is greater than 4, that function value is equal to 1. So we can restate our function this way. We're not looking for the limit as x goes to 4 of the absolute value of x minus 4 over x minus 4. We can instead say we're looking for the limit as x goes to 4 of the function defined by this piecewise function. -1 when x is less than 4, +1 when x is greater than 4. Now, before we evaluate this, let's just take a moment. You might be skeptical here and say, wait a second, how can that be? I'd like to just take a moment or two to plug in a few values. Let's imagine a number less than 4. I'm just going to make up the number -9. Let's let x be -9. The absolute value of x minus 4 over x minus 4 will equal the absolute value of -9 minus 4 over -9 minus 4. Well, that'll be the absolute value of -13 over -13. The absolute value of -13 is 13. 13 over -13 is -1. In other words, we randomly chose an x value that's less than 4, and we discovered that the y value, that the value of absolute value of x minus 4 over x minus 4 is -1. If we picked another one, let's try -22. Plug that in. Absolute value of -22 minus 4 all over -22 minus 4 is going to equal the absolute value of -26 all over -26, which is 26 over -26, which is -1. No matter what value you put in less than 4, it's going to equal -1. Strange. And similarly, let's put a value in greater than 4. So let's try the number 37. Let x equal 37. So the absolute value of 37 minus 4 over 37 minus 4 is the same as the absolute value of 33 over 33. Well, the absolute value of 33 is 33, so we get 33 over 33, which is 1. Okay? So no matter what value you pick that's greater than 4, you're going to get a value of 1. So hopefully, what I've done is enough to, until you get used to these ideas, to at least convince you that that is actually an accurate description of the function. So seeing that function in front of you, we see that as we approach an x value of 4 from the left, our y values are getting infinitely close to -1. In fact, they are -1 the whole time. But as we approach an x value of 4 from the right, our y values are getting infinitely close to 1. Okay? And so what's happening is we see that the one-sided limit as we approach -4 from the left doesn't equal the one-sided limit as we approach -4 from the right, and therefore the limit doesn't exist. So the limit we were asked to find doesn't exist.